Something distant is altering its path, and we might be its intended destination? The interstellar interloper, designated 3IATLAS, once dismissed as merely another frozen celestial wanderer, has commenced a subtle yet consistent acceleration. This newfound momentum is directed along a trajectory that, under normal circumstances, should be utterly unachievable. Based on a series of independent assessments, corroborating Avi's initial observations of a non-gravitational acceleration phenomenon near its closest approach to the Sun, a sustained push for merely 50 days could augment its velocity by 86 meters per second. This alteration, remarkable in its own right, would synchronize its path with Earth on the 19th of December, 2025. The critical question remains, is this an act of physics or a deliberate propulsion? Is it a mere consequence of dust and solar influence or a meticulously orchestrated maneuver? Concurrently with this positional shift, a distinct radio frequency has emerged, 1.44 gigahertz. These faint rhythmic pulses, almost mathematical in their cadence, are traversing the void, seemingly as a response. Could this signify a form of communication or coordination? Remain with me, because by the conclusion of this presentation, you will grasp precisely why some of the world's most brilliant scientific minds are now contemplating the unthinkable. 3IATLAS is not simply passing by. It may very well be actively navigating toward us. If this cosmic enigma continues to captivate your curiosity as it has mine, please consider expressing your engagement by hitting the like button and subscribing to ensure you don't miss any updates as this extraordinary event unfolds in real time. Part 1. Unpacking the claim. A celestial body is approaching, currently somewhere in the expanse between Mars and Jupiter. An entity originating from beyond our solar system is traversing our celestial neighborhood. This is not conjecture. It is not a work of fiction. The object is demonstrably real, possessing a formal designation, 3IATLAS. Its initial detection occurred on the 1st of July, 2025, by the Asteroid Terrestrial Impact Last Alert System, or ATLAS, situated in Chile. What sets this object apart is not merely its extraterrestrial origin, but its current, potentially groundbreaking activity. A series of posts disseminated across X, the social media platform formerly recognized as Twitter, presented a startling calculation put forth by an independent researcher. This assertion has arrested the attention of many. If 3IATLAS maintains a non-gravitational acceleration averaging approximately 0.02 millimeters per second, squared for a duration of about 50 days, it could achieve a velocity modification of roughly 86 meters per second. This projected velocity change, according to the claim, would bring the object into alignment with Earth around the 19th of December, 2025. To reiterate, a potential alignment with our planet. The post delved further, positing this was not a random occurrence, but rather indicative of deliberate navigational adjustments. They even referenced 1.44 gigahertz emanations, suggesting alleged communications and possible course corrections, perhaps even a dialogue between an extraterrestrial probe and an entity in proximity to Mars. Before you dismiss this as another unsubstantiated conspiracy theory, let us examine the established facts. The object's existence is confirmed. Its orbital path is hyperbolic, signifying it is not gravitationally tethered to our Sun. It has indeed originated from interstellar space. Its perihelion, the point of closest approach to the Sun, occurred around the 30th of October, 2025. Crucially, there are documented reports of non-gravitational acceleration. This implies the object is exhibiting motion that cannot be solely attributed to gravitational forces. Non-gravitational acceleration is not an inexplicable phenomenon. It represents physics that we may not yet fully comprehend within this specific context. When a celestial body deviates from a trajectory predicted by gravity, an external force must be at play. Typically, this force is attributed to outgassing. Comets frequently exhibit this behavior. Frozen volatiles sublimate into gas, expelling outward in jets that impart a minute propulsion. While 0.02 millimeters per second squared may sound negligible, It is approximately 150,000th of Earth's gravitational pull. However, in the vacuum of space over extended periods of days and weeks, even minuscule forces can accumulate significant effects. Herein lies the intrigue. This marks only the third confirmed interstellar object ever identified. The first, Oumuamua, discovered in 2017, was a cigar-shaped enigma that ignited extensive scientific debate. The second, Borisov, observed in 2019, presented as a conventional comet. Now we have 3IATLAS, and unlike its predecessors, this object is displaying characteristics that are prompting profound and perhaps unsettling questions. What are the stakes involved? If this is merely an unusual comet, it still holds considerable scientific value, offering a tangible sample from another star system passing through our own, providing insights into planetary formation processes elsewhere in the galaxy. However, if the observed acceleration is indeed intentional, if this object is being guided by an external agency, then we are confronted with an event of an entirely different magnitude. We are facing the remote yet distinct possibility of an artificial construct originating from another civilization. The objective of this investigation is straightforward. We will meticulously examine the claim, scrutinizing the data, the underlying assumptions, the mathematical calculations, and the speculative leaps involved. We will differentiate between established knowledge and conjecture. Furthermore, we will look ahead to the developments anticipated in late 2025 and early 2026, a period when further observations could either validate or definitively refute this hypothesis. This endeavor is not about fostering alarmism. It is about discerning objective reality, exploring potential scenarios, and separating meaningful signals from mere background noise. The universe in its vastness is replete with phenomena that elude our current understanding. Periodically, an anomaly emerges that challenges our established models. 3IATLAS might be one such instance, or it could simply be a particularly atypical interstellar comet exhibiting outgassing in a manner that appears anomalous to us. By the conclusion of this presentation, you will be equipped to ponder a crucial question. Is it a natural comet, an alien probe, or something yet to be categorized? You will possess the necessary framework to form your own informed judgment, comprehending the scientific principles, the mathematical underpinnings, the observational strategies, and the broader implications at play. You will also be aware of what to anticipate in the ensuing months. Our investigation will be structured into 3 distinct segments. The initial act will focus on presenting the core claim and the available data. We will explore the fundamental nature of 3IATLAS, the quantitative evidence, and the assumptions underpinning the scenario of an Earth intercept. The second act will delve into more speculative realms, examining controversies, contrasting natural versus exotic explanations, and analyzing the social media narratives that have amplified this story. The third act will broaden our perspective to encompass recent advancements in space science, artificial intelligence, and radio astronomy, thereby contextualizing 3IATLAS within the cutting edge of scientific discovery. We will then conclude with an overview of future expectations and what specifically you should monitor. One final preliminary point before we proceed. The universe operates independently of our comfort or preparedness. For the majority of human history, we harbored the belief that we were singular entities, that Earth occupied a central position in all things, and that the cosmos revolved around us. Every significant discovery since then has served to temper this anthropocentric view. We learned that Earth orbits the Sun, that our Sun is but one among billions, and that galaxies extend beyond enumeration. Now we are learning that objects from other star systems are capable of visiting us. What transpires when one of these visitors exhibits behavior that defies our immediate comprehension? Next, we will examine the actual data to enable you to assess the validity of this claim for yourself. Part 2. Deciphering the data. The discovery of 3IATLAS occurred on the 1st of July, 2025. The Atlas system, a network of telescopes in Chile designed for identifying near-Earth objects, detected an anomaly. Initially, it appeared as a faint point of light traversing the sky. However, subsequent orbital computations revealed something extraordinary. Its trajectory was hyperbolic. A hyperbolic trajectory signifies that the object is not gravitationally bound to our sun. It is traveling with such velocity that solar gravity cannot capture it. It originated elsewhere, passed through our solar system, and is now departing back into the void between stars. This is the defining characteristic of an interstellar visitor. The designation 3A was assigned, marking it as the third confirmed object of interstellar origin. Let us now consider its orbit. Perihelion, the closest approach to the Sun, took place around the 30th of October, 2025, at a distance of approximately 1.36 to 1.4 astronomical units. Recall that 1 astronomical unit is the mean distance between Earth and the Sun, roughly 150 million kilometers. Therefore, at perihelion, 3IATLAS was situated between 203 and 210 million kilometers from the Sun, placing it roughly within the orbital path of Mars. Its closest predicted approach to Earth is scheduled for the 19th of December, 2025, at a distance of approximately 1.8 astronomical units, translating to about 268 to 270 million kilometers. For perspective, the Moon is approximately 384,000 kilometers from Earth. This object will pass at a distance equivalent to about 700 times the Earth-Moon separation. This is an exceedingly vast distance, far beyond any conventional definition of a close encounter. Now we arrive at the anomaly. In a publication on Medium, Avi Loeb, a distinguished Harvard astrophysicist renowned for his work on Oumuamua and the search for extraterrestrial technology, reported an unusual observation. Astrometric data obtained from the Jet Propulsion Laboratory and the Atacama Large Millimeter Array indicated a deviation from its predicted path. The object was not positioned as expected if gravity alone were dictating its motion. This positional discrepancy amounted to approximately 4 arc seconds, a minuscule angular shift, yet significant when tracking an object across millions of kilometers. Loeb subsequently calculated a non-gravitational acceleration of roughly 0.02 millimeters per second squared. He then applied a momentum conservation equation to investigate potential causes. If outgassing is the primary driver, meaning jets of vapor expelling from the object, then the rate of mass loss would need to be substantial. His calculations suggested that at least 1/16 of the object's mass would need to sublimate over approximately 1 month to generate this observed level of acceleration. Let us pause to consider this. While outgassing itself is not extraordinary, comets routinely exhibit this behavior. As ice transitions directly from solid to gas, sublimation, it escapes the surface, generating a thrust. This is akin to a miniature rocket engine, weak but measurable. The challenge with 3IATLAS lies in its scale. If the object possesses a mass as substantial as some estimates suggest, on the order of tens of billions of tons, then losing 1/16 of that mass within a month should result in a conspicuous cloud of gas and dust, a visible coma, or a tail, observable phenomena. Visually, 3IATLAS has displayed some unusual characteristics. Images indicate a jet-like structure, possibly directed towards the Sun rather than away from it, which is atypical. The object's coloration has also drawn attention. Descriptions characterize it as bluer than the Sun, potentially indicative of ionized carbon monoxide rather than typical dust. These are suggestive clues, but not definitive proof. Comets can exhibit peculiar behaviors, and interstellar comets even more so. What does the data not reveal? Loeb himself does not assert that the object is on a trajectory to intersect Earth. He does not claim it is intentionally maneuvering toward us. The data demonstrate an acceleration and a positional offset, indicating something intriguing is occurring. The leap to an Earth intercept scenario, suggesting intentional steering, originates elsewhere. It stems from social media posts that have taken Loeb's quantitative findings and extrapolated them into a dramatic narrative. Herein lies the crucial distinction. The data, while intriguing, are not inherently inexplicable. We're observing a hyperbolic interstellar object exhibiting some degree of outgassing, and a jet structure that falls within the purview of known physics is certainly on the unusual end of the spectrum, but not entirely outside the realm of possibility. The central question is whether the data genuinely support the bold assertion that 3IATLAS is actively altering its course towards Earth, or if real data has been augmented with layers of assumption to arrive at a sensational conclusion. Thus far, what we possess is this: an interstellar object, confirmed and real, an orbit that brings it relatively near Earth, though still at a considerable distance, a non-gravitational acceleration that could be attributed to outgassing or potentially something else, and a calculation demonstrating mathematically how a small, sustained force applied over 50 days could result in a significant change in velocity. Is this sufficient to claim the object is aligning with Earth? This is the pivotal question we will address next by examining the mathematical framework and the assumptions that transform raw data into a compelling narrative. Part 3. Extrapolation to Earth, intercept, mathematics, and assumptions. Let us perform the calculations. The assertion circulating on social media commences with a fundamental equation from classical physics. Acceleration multiplied by time equals velocity change. If a constant acceleration of 0.02 millimeters per second squared is maintained for 50 days, what is the resultant velocity change? 50 days equates to 4,320,000 seconds. Multiplying this by 0.02 millimeters per second squared, which is equivalent to 2 multiplied by 10 to the power of negative 5 meters per second squared, yields approximately 86.4 meters per second. This is the delta V, the change in velocity. The mathematics involved are sound. There is no disagreement regarding the arithmetic itself. Now let us consider displacement. When a constant acceleration is applied over time, it not only alters velocity, but also changes position. The displacement under constant acceleration is calculated as 1/2 multiplied by acceleration multiplied by time squared. Plugging in the figures, 1/2 multiplied by 2 times 10 to the power of negative 5 meters per second squared multiplied by 4.32 times 10 to the power of 6 seconds squared results in approximately 1.87 times 10 to the power of 8 meters, which is equivalent to 187,000 kilometers. This is roughly half the distance from Earth to the Moon. Consequently, the numbers are indeed significant. A modest but continuous thrust applied over 50 days could alter an object's trajectory by hundreds of thousands of kilometers. Within the context of orbital mechanics, this is a substantial deviation. It could influence the point in time at which an object crosses a particular plane. It could alter a predicted close approach distance. It could theoretically transform a distant flyby into a more intimate encounter. However, this is where the assumptions begin to accumulate. The calculation presupposes that the acceleration continues unabated for the entire 50-day period. Is this a valid assumption? We lack definitive knowledge. The acceleration was measured at a specific juncture near perihelion. Whether it persists for weeks or months remains uncertain. Outgassing typically fluctuates in intensity based on an object's proximity to the sun. As an object moves away from perihelion, solar heating diminishes, and consequently the rate of sublimation decreases. The propulsive force might then weaken or cease altogether. The calculation also assumes that the acceleration is applied along a precisely correct vector. Direction is as critical as magnitude. If the thrust is directed sideways, perpendicular to Earth's orbital plane, it might alter the orbital plane, but would not necessarily result in a significant change in the closest approach distance. If the thrust is prograde, increasing the object's speed, it affects the arrival time. If it is retrograde, decreasing its speed, the outcome is similar. If the thrust is radial, pushing either towards or away from the sun, it influences the semi-major axis and eccentricity of the orbit. Without precise knowledge of the acceleration's direction, integrating the velocity change into a predictive trajectory model is inherently speculative. Timing constitutes another crucial assumption. The object must exert this thrust at the opportune moment and in the correct direction. so that the resulting path intersects Earth's orbit precisely when Earth is present at that intersection point. Earth travels at approximately 30 kilometers per second in its orbit around the Sun, covering vast distances in mere days. Intercepting a moving target necessitates extraordinary precision in both timing and vectoring. A displacement of 187,000 kilometers might indeed shift the point of intersection. However, if Earth is not at that location at the designated time, the intercept will not occur. Then there is the matter of energy and mass. If the object is as massive as estimates indicate, tens of billions of tons, sustaining continuous thrust demands immense energy reserves. The source is natural outgassing. The rate of mass loss must be exceptionally high, as calculated by Loeb. If it is artificial, it implies the presence of a propulsion system capable of prolonged thrust application. Either scenario stretches the boundaries of plausibility unless corroborated by supporting evidence. Finally, we must consider the impact of perturbations. Space is not an absolute vacuum. Solar radiation pressure, the gravitational influence of planets, the solar wind, and even the Aohovsky effect can all subtly influence the trajectory of a smaller celestial body. The simplified calculation assumes these factors are negligible or effectively cancel each other out. In reality, however, they introduce noise and uncertainty. A purely deterministic 50-day propulsion event represents an idealized scenario. Allow me to employ an analogy. Imagine you are driving on a highway. You know you can accelerate your speed by 60 kilometers per hour. This is analogous to knowing your delta V. However, merging into the correct lane at the opportune moment to reach a specific exit requires more than just increased speed. You must ascertain the exit's location, the speed of surrounding traffic, the precise moment to accelerate, and the correct steering adjustments. The arithmetic of velocity change is one aspect. The geometry and temporal dynamics of orbital mechanics are an entirely different matter. The extrapolation presented on social media assumes the acceleration was directed in a manner conducive to an Earth intercept. We have no evidence to support this premise. The data indicate some form of acceleration, but not its vector relative to Earth's orbit. The claim then adds, this acceleration is purposeful and Earth targeting. This is an interpretation layered upon the data, rather than a direct derivation from it. Here's what we know versus what is assumed. We know a non-gravitational acceleration is occurring. We know it is subtle, yet measurable. We know the object's trajectory brings it into relative proximity with Earth in December. We assume the acceleration will persist for 50 days. We assume it is directed appropriately. We assume the timing will align. We assume no other external factors will interfere. And we interpret all of these assumptions as indicative of intentional maneuvering towards Earth. Each assumption represents a link in a chain. If even one link breaks, the entire claim falters. The question is not whether the mathematical calculation is correct. It is. The question is whether the real-world conditions conform to these assumptions. Next, we will examine the actual trajectory and missed distance to ascertain whether a velocity shift of 86 meters per second could realistically transform a 270 million kilometer flyby into something more alarming. Part 4. Object trajectory and missed distance. The official figures are unambiguous. According to NASA and the European Space Agency, 3IATLAS is projected to pass Earth at a distance of approximately 1.8 astronomical units on the 19th of December 2025. This translates to roughly 268 to 270 million kilometers. To provide a sense of scale, 1 astronomical unit represents the average distance between Earth and the Sun, approximately 150 million kilometers. Therefore, at 1.8 astronomical units, the object will be nearly twice the Earth's orbital distance at its closest approach. This is not considered a close proximity by any standard employed in planetary defense. An object is deemed potentially hazardous if its orbit brings it within 0.05 astronomical units of Earth, approximately 7.5 million kilometers. 3IATLAS will pass at a distance exceeding 30 times that threshold. Both NASA and ESA have explicitly stated that the object poses no threat to Earth. Therefore, how do we account for missed distances in orbital mechanics? When an object approaches on a hyperbolic trajectory, its path is determined by its velocity, direction, and the gravitational influences it encounters. The missed distance essentially represents the closest point of approach, calculated based on the object's trajectory relative to Earth's position at a specific moment in time. For 3IATLAS, this calculation indicates a missed distance of 1.8 astronomical units on the 19th of December. Now let us address the central inquiry. Could a velocity change of 86 meters per second significantly alter that missed distance? The answer is both yes and no, depending on the context. Yes, in principle, a delta V of 86 meters per second applied over 50 days could indeed shift the object's trajectory by hundreds of thousands of kilometers. As previously calculated, the displacement could be in the vicinity of 187,000 kilometers. This is not an insignificant alteration. In orbital mechanics, minor adjustments in velocity, particularly when applied early in an object's trajectory, can lead to substantial positional changes over time. However, no. Transforming a missed distance of 270 million kilometers into an Earth impact would necessitate a considerably greater delta V, unless the vector and timing of the impulse were extraordinarily fortuitous. The object is traveling at approximately 60 kilometers per second, which equates to 60,000 meters per second. 86 meters per second represents less than 0.15% of its total velocity. To modify the trajectory sufficiently to alter the missed distance from 270 million kilometers to zero would require either a substantially larger delta V or an almost perfectly aligned thrust direction and timing. The direction of the thrust is paramount. Envision the object's trajectory as a line in space. If you apply a force perpendicular to the velocity vector, you alter the orbital plane. This might result in a lateral shift of the path by 100,000 kilometers, but it would not necessarily bring it closer to Earth. If you apply force along the velocity vector, either forwards or backwards, you change the arrival time. The celestial body may approach Earth's orbital plane sooner or later, but this still doesn't guarantee a close encounter unless our planet happens to be at that precise location. Altering the shape of an orbit, its eccentricity, and the closest approach distance occurs when you exert force radially toward or away from the Sun. In orbital mechanics, there's a concept known as the B-plane, which is a virtual plane positioned perpendicular to an object's incoming path. This plane is used to determine where an object will intersect relative to a specific target. Imagine it like a dartboard. The bullseye represents Earth. The trajectory of the object pierces this plane at a certain point, and the distance from the bullseye to that intersection point signifies the missed distance. A minor adjustment in velocity can shift the location where the object crosses the plane, but moving from the periphery of the dartboard to its center demands a very precise application of force. Without precise knowledge of the direction of 3IATLAS's non-gravitational acceleration relative to Earth's position, we cannot ascertain how significantly the missed distance would actually change. The assertion circulating on social media presumes that the applied force is in the optimal direction, a significant presumption. Furthermore, the object's mass is a critical factor. Estimations suggest 3IATLAS is substantial, potentially exceeding 33 billion tons with a diameter spanning several kilometers. Propelling a celestial body of such magnitude through natural outgassing presents considerable challenges. It is akin to attempting to steer a mountain by evaporating ice from its surface. If the mechanism were artificial, it would imply the presence of an engine or propulsion system of immense power. In either scenario, the underlying physics presents significant hurdles. Scientists from NASA and the International Astronomical Union, who have access to complete astrometric data and sophisticated orbital models, have concluded that the object is not on a collision course with Earth. They meticulously account for inherent uncertainties, external influences, and potential non-gravitational forces. Their models consistently indicate a safe trajectory. Had the data suggested otherwise, even a marginal possibility of impact, it would have triggered widespread alarm. Planetary defense systems are specifically designed to identify and monitor celestial objects that pose a potential threat. 3IATLAS is not currently listed among these potential hazards. Therefore, a reality check on the missed distance boils down to this. The alignment of celestial bodies and the timing of events make an Earth impact scenario exceedingly improbable at this juncture. The object would require substantially greater velocity adjustment applied in a highly specific direction at a very particular moment to transform a nearly 270 million kilometer flyby into a dangerous encounter. While the numbers might appear alarming if one focuses solely on the arithmetic of delta V, the comprehensive picture encompassing orbital mechanics, temporal factors, and missed distances all point towards a distant passage. This does not diminish the object's scientific interest. On the contrary, its non-gravitational acceleration, unique characteristics, and status as an interstellar visitor render it highly valuable from a scientific perspective. However, the notion of an Earth intercept course, the claim that it is directly aligned with our planet, remains speculative. Moving forward, we will delve into the intensified observational campaign currently underway, the array of telescopes focused on 3IATLAS, and the verifiable predictions that will soon clarify whether this object is a comet, a probe, or something in between. Part 5. Observational campaign and testable predictions. The forthcoming months are pivotal. Between now and early 2026, 3IATLAS will undergo rigorous scrutiny. Telescopes across the globe and in orbit are already tracking its movement. The closest approach to the Sun, known as perihelion, occurred around October 30th, 2025, when the object reached its nearest proximity to the Sun. It is now traveling outbound, progressing towards its close encounter with Earth on December 19th. This period represents the crucial observational window, and it is finite. Once the object recedes beyond Earth and ventures deeper into the outer solar system, it will diminish from view. The primary instruments involved in this extensive observation effort comprise some of humanity's most advanced technological achievements. The Hubble Space Telescope is capable of capturing high-resolution imagery across visible and ultraviolet wavelengths. The James Webb Space Telescope, with its infrared capabilities, can detect thermal signatures and analyze the composition of any surrounding gas or dust. Terrestrial observatories such as the Very Large Telescope in Chile and the KEK Observatory in Hawaii are also contributing valuable data. Radio telescopes are actively monitoring for any unusual missions. Furthermore, instruments aboard Mars orbiters may capture a fleeting glimpse as 3IATLAS passes relatively near the red planet. An interesting celestial alignment also presents itself. On November 4, 2025, the European Space Agency's Jupiter Icy Moons Explorer, designated JUICE, will traverse a path approximately 64 million kilometers from 3IATLAS. While this proximity is insufficient for a dedicated close-up study, JUICE's instruments may still be able to acquire data from this distance. Every piece of information gathered contributes to the overall understanding. Avi and his colleagues have formulated verifiable predictions. These predictions are contingent upon whether the observed non-gravitational acceleration is attributable to natural outgassing or some other phenomenon. If outgassing is the cause, a significant loss of mass should be evident. Lowe's calculations indicated that at least 1/16 of the object's mass would need to sublimate over approximately 1 month. This process should generate a substantial cloud of gas and dust, a visible coma, and likely a tail extending behind the object as the solar wind propels the particles away. Consequently, the initial prediction is straightforward. If the acceleration is a natural occurrence, telescopes should detect a vast envelope of gas and dust. Spectroscopic analysis should reveal the presence of volatile compounds such as water, carbon monoxide, carbon dioxide, or methane. The object should exhibit characteristics consistent with a comet, displaying all the telltale signs of activity driven by sublimation. Conversely, if no substantial cloud is observed and the mass loss is minimal or absent, then the hypothesis of natural outgassing is significantly weakened. This outcome would be of considerable importance, suggesting that the acceleration originates from an alternative source, one that does not necessitate the expulsion of vast quantities of material. In such a scenario, non-natural or even technological explanations would gain greater plausibility. Key measurements to monitor include astrometric residuals, which represent the discrepancies between the object's actual position and its predicted position based solely on gravitational influences. These residuals illuminate the magnitude and direction of any non-gravitational forces. As more observational data becomes available in the coming weeks, astronomers will refine the orbit and quantify the acceleration with enhanced precision. Spectroscopy remains another crucial analytical technique. By dispersing the light emitted by the object into its constituent wavelengths, scientists can identify the specific molecules and atoms present. 3IATLAS has already been noted for its unusual coloration, described as bluer than the sun. This could signify the presence of ionized carbon monoxide, a spectral signature characteristic of certain comet types, or it might indicate something else entirely. Detailed spectroscopic analysis will provide deeper insights into its composition and whether it aligns with known cometary chemical profiles. Visual observation is equally significant. The morphology of any developing coma or tail, the structure of emanating jets, and the presence of asymmetries all offer valuable clues. Some reports have mentioned an anti-tail, a jet directed towards the sun rather than away from it. While unusual, this phenomenon is not unprecedented. Comets occasionally display features pointing forward due to observational geometry or rotational effects. High-resolution imaging will clarify whether these observed phenomena are consistent with natural processes. Finally, radio astronomy plays a role. Social media reports have alleged that the object emitted signals at 1.4 gigahertz, purported to be communications or course correction commands. This claim is entirely unverified, yet radio telescopes will still be actively listening. Should any anomalous emissions be detected, regardless of frequency, they will be systematically recorded and analyzed. While radio signals from comets are infrequent, they are not impossible, often being linked to plasma interactions. A strong structured signal, however, would represent a considerably different situation. This observational campaign is not without its challenges. The timing and geometrical alignment are critical, particularly around the object's perihelion. During this period, 3IATLAS was in close proximity to the sun in the sky, making observation difficult due to intense solar glare. As it now moves away from the sun and towards Earth, its visibility improves. However, by late December, after its closest approach to our planet, it will begin to fade as it travels further from both the sun and Earth. The observational window is thus quite narrow. Environmental conditions, telescope availability, financial resources, and interagency coordination all factor into the equation. Not every telescope can be utilized every night. The subsequent processing and analysis of collected data, followed by peer review and publication, are time-consuming processes. Scientific progress inherently proceeds at a slower pace than the dissemination of information on social media. While claims can propagate rapidly, the rigorous confirmation or refutation of these claims through observation requires weeks or months. Nevertheless, this is an exhilarating period. We are observing a visitor from another star system in real time. The same sophisticated instruments that probe distant exoplanets and investigate the chemical makeup of alien atmospheres are now directed towards an object traversing our own cosmic neighborhood. This represents a rare confluence of opportunity and technological capability. By early 2026, we should possess definitive answers. If 3IATLAS behaves like a typical comet, exhibiting extensive outgassing, a prominent coma, a tail, and spectroscopic signatures of volatile compounds, then the natural explanation will be substantiated. The observed non-gravitational acceleration would simply be attributed to a comet exhibiting its characteristic behaviors, perhaps more pronounced due to its interstellar origin and composition. However, If the observations reveal minimal mass loss and absence of a significant coma, and yet the acceleration persists or displays directional characteristics inconsistent with jetting, then we face a scientific quandary, not a catastrophe, but a perplexing puzzle that does not readily fit within our established theoretical frameworks. At that point, the discourse will shift. At that juncture, more extraordinary hypotheses, which we will explore next, will transition from mere conjecture to subjects demanding serious scientific consideration. The subsequent phase of this investigation will examine the dichotomy between natural and artificial origins, the influence of social media in amplifying unsubstantiated claims, and the potential implications if 3IATLAS proves to be something other than a comet. Part 6. Non-gravitational acceleration, natural explanations. Comets are often described as dirty snowballs, a simplification commonly used in introductory astronomy. The nucleus of a comet is a composite of ice, rock, and organic materials. When a comet approaches the sun, solar radiation heats its surface, causing the ice to sublimate, transitioning directly from a solid to a gaseous state without passing through a liquid phase. The escaping gas carries dust particles along with it, forming a luminous cloud known as a coma, and frequently a tail that trails away from the sun. This outgassing process not only creates a spectacular visual display, but also generates thrust. The momentum of the expelled gas molecules exerts a reactive force on the comet itself, much like a leaky balloon darting around a room. While the effect is subtle, it is measurable and is referred to as a non-gravitational force, a phenomenon that astronomers have been detecting and modeling for decades. Therefore, when Avi reports a non-gravitational acceleration of 0.02 millimeters per second squared for 3IATLAS, the initial assumption is that it is a result of outgassing. This is the default hypothesis, the most straightforward explanation. However, the finer details are important. Loeb applied a momentum conservation equation to estimate the mass loss required to produce this observed acceleration. The formula is quite direct. The force exerted on the comet is equivalent to the rate of mass loss multiplied by the velocity of the outflowing gas. Since force equals mass times acceleration, one can rearrange this equation to solve for the mass loss rate. If the outflow velocity is a few hundred meters per second, typical for cometary jets, and the acceleration is 0.02 millimeters per second squared, it is possible to calculate the rate at which the comet is losing mass. The result is striking. If 3IATLAS possesses a mass of approximately 30 billion tons, the calculations suggest it would need to shed roughly 5 billion tons per month to sustain such an acceleration. This equates to approximately 1/16 of its total mass being lost within a 30-day period. Over several months, the comet would effectively evaporate a significant portion of itself. This represents an immense rate of mass loss, which should be visibly apparent. Astronomers would anticipate observing a vast coma, a massive cloud of gas and dust enveloping the nucleus, and a prominent tail. Spectroscopic analysis should reveal abundant volatile substances. Yet the observations conducted thus far present a more subtle picture. There are reports of a jet directed towards the sun, and the object's color is unusually blue, more so than expected. However, a colossal coma commensurate with this level of mass loss has not yet been definitively observed. This does not necessarily invalidate the natural explanation. Comets exhibit variability. Outgassing can occur episodically, influenced by rotation, the exposure of fresh, icy material, or the collapse of surface layers. It is plausible that the high mass loss rate was a transient event, a burst of activity near perihelion that has since subsided. Alternatively, the gas might be escaping through a concentrated jet rather than dispersing uniformly, making the coma less conspicuous from Earth. It is also possible that the composition of the emitted gas renders it transparent, or that it carries minimal dust, thereby reducing its visibility. The coloration, described as bluer than the sun, is particularly intriguing. It may indicate the presence of ionized carbon monoxide, a molecule that can dominate the spectral output of certain comets. Carbon monoxide ice is more volatile than water ice, sublimating at lower temperatures and at greater distances from the sun. An interstellar comet, having formed in a different stellar environment, might possess a distinct composition, potentially richer in carbon monoxide or other exotic ices compared to comets originating within our solar system. Some images appear to depict an anti-tail, a feature pointing towards the sun rather than away from it. While rare, this phenomenon is not impossible. It can arise from the geometrical perspective of observation, where we view the comet from an angle that makes dust particles in the orbital plane appear to be directed forward. Alternatively, it could represent a genuine jet originating from the front of the comet, driven by rotation or localized heating. The natural explanation necessitates that all these elements coalesce coherently. High mass loss, unusual composition, episodic outgassing, and geometrical effects all contribute to a complex scenario. However, comets are inherently complex objects, and their behavior is not uniform. An interstellar comet formed in another star system under different conditions could easily deviate from the patterns observed in solar system comets. The object's dimensions and mass also warrant consideration. Estimates suggest a diameter of at least several kilometers, possibly exceeding 5 kilometers, and a mass surpassing 30 billion tons. This indicates a comet of considerable size. Accelerating a body of such immense mass through outgassing requires extraordinary energy and material expenditure. It is akin to attempting to propel a large cargo ship by jettisoning its cargo. While achievable, it necessitates the rapid expulsion of a substantial quantity of material. Analogies can be helpful here. Imagine a colossal container ship losing half of its cargo over a month to achieve a slight increase in speed. This is conceivable, but would undoubtedly result in a dramatic spectacle with containers visibly strewn across the water. There would be evidence of widespread debris. Similarly, if 3IATLAS is losing 1/16 of its mass within a month, we would expect to observe tangible evidence, such as gas, dust, and a luminous envelope. What would constitute definitive support for the natural explanation? The detection of a large coma consistent with the projected mass loss rate. Spectroscopic confirmation of the presence of water, carbon monoxide, carbon dioxide, or other volatile compounds in the expected abundances. Imaging that reveals a classic cometary structure, possibly including multiple jets and a tail. Crucially, the acceleration should exhibit a correlation with the object's distance from the sun. As the comet experiences less solar heating, its outgassing should diminish, and consequently its acceleration should decrease. If this does not occur, if the acceleration persists or even intensifies, as the comet moves further from the sun, it would serve as a significant warning sign. At present, the hypothesis of natural outgassing remains plausible but demanding. The required rate of mass loss is exceptionally high, and the observational evidence is presently inconclusive. The object's considerable size and mass further complicate this scenario. However, comets have surprised us in the past. Oumuamua surprised us with its anomalous acceleration and elongated shape, while Borisov presented as entirely unremarkable in appearance. It is possible that 3IATLAS is simply the next instance of such surprise, a comet exhibiting extreme characteristics that push the boundaries of our conventional understanding. Alternatively, it might represent something entirely different. This leads us to our next area of inquiry: the speculative yet scientifically intriguing hypotheses concerning artificial technological origins. Part 7. Non-gravitational acceleration. Exotic technological hypotheses. What if the observed acceleration is not a natural phenomenon? What if 3IATLAS is not merely a comet behaving in a conventional manner? What if it is something engineered, something deliberately sent, something designed? Avi and his colleagues have authored a paper titled, "Is the Interstellar Object 3IATLAS Alien Technology?" This is not a flippant inquiry, but a serious scientific investigation framed within the parameters of what can be plausibly ruled in or out. The paper explores the possibility that the object is a manufactured artifact, perhaps a probe dispatched from an extraterrestrial civilization. Several convergent factors prompt this line of inquiry. Firstly, the observed non-gravitational acceleration. If it cannot be definitively explained by outgassing, or if the outgassing explanation becomes implausible due to the exceptionally high mass loss rate required, then alternative mechanisms must be considered. Secondly, the estimates regarding the object's size and mass. A large, massive body experiencing measurable acceleration implies a significant transfer of energy and momentum. Thirdly, its trajectory. Loeb notes that the object's path through the inner solar system, its temporal progression, and its alignment with Earth's orbital plane are statistically anomalous. While not impossible, such a confluence of factors is unlikely if it were merely a random visitor from interstellar space. The energetic requirements merit detailed examination. For an object with a mass measured in tens of billions of tons to sustain an acceleration of 0.02 millimeters per second squared for a period of weeks, the required thrust is substantial. Force equals mass times acceleration. Plugging in 10 to the power of 13 kilograms and 2 times 10 to the power of negative 5 meters per second squared yields a force of approximately 200,000 newtons. This is equivalent to the sustained thrust of a small rocket engine. However, solar sails, while potentially capable of providing propulsion, are generally inefficient unless they are exceptionally large and highly reflective. Calculations suggest that a sail of sufficient size to accelerate this mass would need to span kilometers and be precisely oriented. Alternatively, a more advanced propulsion system, such as an ion drive, a fusion engine, or a technology yet to be conceived, might be involved. The mention of 1.4 gigahertz pings in social media reports adds another dimension to this hypothesis. The frequency of 1.4 gigahertz holds particular significance in the search for extraterrestrial intelligence because it corresponds to the hydrogen line, a natural emission frequency of neutral hydrogen atoms. This frequency is sometimes referred to as the water hole in radio astronomy, representing a relatively quiet band within the electromagnetic spectrum conducive to signal propagation through space with minimal interference. If an advanced civilization intended to transmit a signal, 1.4 gigahertz would logically be a favored choice. However, a critical issue arises. There is no publicly verifiable detection of such pings originating from 3IATLAS. Radio telescopes continuously monitor the sky, and any strong structured signal emanating from the object would have almost certainly been detected. The claim remains unsubstantiated, existing in the realm of pure speculation. Nevertheless, let us entertain the hypothesis, assuming, for the sake of argument, that 3IATLAS is an artificial probe. What might its purpose be? Reconnaissance or observation are plausible objectives. It could have been drifting through space for millions of years, a relic of a long extinct civilization, still executing its programmed mission to survey star systems. Alternatively, it might be an active entity, deliberately altering its course to investigate points of interest. Could it intentionally maneuver itself to intercept Earth? In essence, yes, if it possesses the requisite capabilities. A probe equipped with a functional propulsion system could, in principle, modify its trajectory. However, the delta V required to transform a missed distance of 270 million kilometers into an actual intercept far exceeds the observed 86 meters per second. Velocity changes on the order of kilometers per second applied with precise timing and direction would be necessary. This implies a considerable amount of thrust sustained over an extended period. Loeb has also discussed the dark forest hypothesis in the context of 3IATLAS. The dark forest concept, popularized by science fiction author Liu Cixin, posits that the universe teems with civilizations, yet they remain silent to avoid detection by potentially hostile neighbors. Revealing one's presence could invite annihilation, leading all civilizations to adopt a strategy of concealment within the cosmic dark forest. Loeb suggests that if 3IATLAS is indeed a probe, its actions might stem from a cautious methodology, observing from a considerable distance rather than initiating direct contact. This is purely speculative, built upon layers of assumptions. The first assumption is that the object's acceleration is not a natural phenomenon. The second is that it is artificial. The third assumption is that it is being controlled by an intelligent entity. The fourth is that this intelligence exhibits caution or has a specific agenda regarding Earth. Each subsequent assumption diminishes the likelihood of the entire scenario. What would constitute definitive proof of a technological origin? Several indicators come to mind. Unusual radio transmissions, particularly those exhibiting structured patterns or containing meaningful information, propulsion signatures that suggest sustained acceleration without a corresponding loss of mass or expulsion of gas. Minimal mass loss accompanying significant acceleration, which would defy the principles of rocket propulsion unless an external energy source is involved. Highly reflective surfaces implying manufactured materials rather than natural rock or ice, and changes in orientation or posture that cannot be attributed to random tumbling. Should observations reveal any of these characteristics, the discourse would shift dramatically. The extraordinary hypothesis would transition from fringe speculation to a plausible explanation warranting thorough investigation. However, if none of these telltale signs emerge and the object continues to behave like a peculiar but natural comet, then the technological hypothesis would recede into the background. The implications are profound. If the probe scenario proves true, it would definitively establish that humanity is not alone. It would signify that another civilization has achieved a level of technological advancement sufficient to dispatch objects across interstellar distances. This would inevitably raise questions about their intentions, their lifespan, and their ultimate fate. Are they still present? Did they dispatch a single probe or a multitude? Is 3IATLAS an ancient artifact or a recent creation? Nevertheless, the immense stakes do not inherently validate the hypothesis. Extraordinary assertions demand extraordinary evidence, and currently, the evidence is, at best, ambiguous. The observed non-gravitational acceleration is a verifiable fact, but its origin is not definitively non-natural. The object's trajectory is unusual, yet not impossible for a random interstellar visitor. The reported radio signals remain uncorroborated. The absence of a substantial coma is suggestive, but not conclusive. Science operates by testing hypotheses, formulating predictions, and comparing them against observational data. The technological hypothesis also generates predictions. The absence of a large gaseous cloud due to a lack of outgassing, consistent acceleration even as the object moves away from the sun, indicating a propulsion system not reliant on solar energy, and the potential for radio emissions or other non-thermal signatures. Over the coming months, observational data will be crucial in verifying these predictions. Should the object ultimately be identified as natural, valuable knowledge will still be gained. We will have advanced the frontiers of cometary science, explored the chemistry and dynamics of interstellar visitors, and tested our models against an exceptional case. If, however, the object proves to be artificial, that discovery would represent the most significant in human history. Regardless of the outcome, the observations expected in late 2025 and early 2026 promise to be fascinating. Subsequently, we will examine how this narrative evolved, specifically how social media transformed scientific data into a story of alien interception and conspiracy. Part 8. The social media narrative and conspiratorial framing. The initial post surfaced on X in mid-October 2025, originating from an independent researcher unaffiliated with any major institution. They presented a series of claims centered on the observation that 3IATLAS is accelerating. The assertion was that if its acceleration of 0.02 millimeters per second squared persisted for 50 days, it would accumulate an additional 86 meters per second of velocity. This velocity change, if applied in the correct direction at the opportune moment, could align the object with Earth by December 19, 2025. The claims then escalated, with the researcher positing that the acceleration was not random, but intentional, suggesting the object was maneuvering, correcting its course, and deliberately aiming for Earth. Mentions also arose of 1.4 gigahertz pings detected near Mars, purportedly representing communications or signal exchanges between the object and another entity. The narrative thus shifted from an intriguing scientific anomaly to an alarming scenario of an alien probe targeting us. Let us dissect this piece by piece. The data regarding the acceleration is indeed factual, reported by Avi Loeb and substantiated by astrometric observations from reputable sources. The arithmetic calculating that 0.02 millimeters per second squared multiplied by 50 days yields 86 meters per second is also correct, representing basic physics without error. However, the subsequent assumptions are where interpretation diverges from verified fact. The assumption that the acceleration will continue for precisely 50 days, that it is directed toward Earth, and that the timing aligns perfectly with Earth's orbital position are all unsubstantiated. These are extrapolations, mere guesses derived from limited data. The interpretation that the object is aligning itself with Earth marks the transition from data to narrative. Alignment implies intent, suggesting the object is deliberately steering itself toward our planet. There is no empirical evidence to support this assertion. The projected missed distance remains 270 million kilometers, and NASA has stated there is no threat. The geometrical configuration does not support an intercept scenario unless multiple improbable factors coincide. The 1.4 gigahertz pings are also unverified. No major observatory has confirmed any radio emissions from 3IATLAS. If such a signal were present, radio astronomers would undoubtedly be intensely investigating it. While the lack of confirmation does not definitively disprove the existence of the pings, it necessitates that they not be taken seriously without supporting evidence. So how did this narrative gain such momentum? Social media thrives on uncertainty and dramatic storytelling. A scientific anomaly, a gap in our collective understanding, becomes fertile ground for conjecture. Individuals take existing data, overlay their own interpretations, and construct narratives. These narratives propagate more rapidly than scientific explanations because they are inherently more captivating. An alien probe targeting Earth makes for a far more compelling headline than a comet exhibiting unusual outgassing. The underlying psychology is fascinating. Humans are inherently predisposed to identifying patterns, even where none exist. We are drawn to narratives that impose meaning upon chaos. An interstellar object exhibiting unexplained acceleration is not merely a comet behaving oddly. It is perceived as a sign, a message, or perhaps even a warning. This narrative taps into broader societal anxieties concerning the unknown, the vastness of space, and our readiness for potential extraterrestrial contact. Conspiratorial framing further amplifies these sentiments. Once the notion that the object might be artificial takes root, every ambiguity is reinterpreted as evidence. The absence of a visible coma is presented as proof it's not a comet. Its unusual color suggests engineered materials. Its trajectory implies deliberate targeting, and the lack of official confirmation of radio pings is construed as a cover-up. Consequently, the narrative becomes self-sustaining and resistant to contradictory evidence. This phenomenon is not unique to 3IATLAS. Objects like Oumuamua underwent a similar cycle. A peculiar object emerges. Scientists acknowledge their incomplete understanding, and the internet readily fills those voids with extraterrestrial explanations. Occasionally, even scientists themselves, like Loeb, contribute to this speculative fervor. Loeb is known for publicly entertaining exotic hypotheses, advocating for the consideration of all possibilities, including technological origins. While such openness is valuable in scientific inquiry, it can also fuel sensationalism. Mainstream media outlets often disseminate these stories, frequently in simplified or exaggerated forms. Headlines proclaiming alien probe may appear even when the accompanying article presents a more nuanced perspective. The New York Post, for instance, published an article quoting Loeb regarding 3IATLAS, framing it as a potential alien engine. This framing is significant, as many readers do not proceed beyond the headline, absorbing the idea that scientists suspect alien involvement, and thus, that becomes the prevailing story. The responsibility in science communication lies in clearly distinguishing between factual data and extrapolated interpretations. The data indicate a non-gravitational acceleration, period. The extrapolation to an Earth intercept, intentional maneuvering, and alien technology represents layered interpretations which, while potentially true, are not established facts. A delicate balance must be struck. On one hand, possibilities should not be dismissed prematurely, as scientific progress often stems from exploring seemingly unlikely ideas. On the other hand, speculation should not be equated with evidence. The assertion that 3IATLAS is aligning itself with Earth does not hold the same weight as the observation of its non-gravitational acceleration. One is a measurement, the other an inference. Social media tends to erode this distinction, conflating all claims, theories, and possibilities. This diminishes the signal-to-noise ratio, leading to debates about whether the object poses a threat without even agreeing on the factual data. Misinformation spreads not necessarily due to deliberate deception, but because the boundary between data and interpretation becomes blurred. This brings us to a meta question. Are we adequately prepared for the possibilities? What if the object, while natural, is extraordinarily peculiar, pushing the boundaries of cometary physics? Or what if it is artificial, confirming our non-solitary existence? How, as a society, do we process information in an environment where truth and speculation coexist seamlessly within the same digital feeds? The social media discourse surrounding 3IATLAS serves as a compelling case study of the intersection between science and narrative. The subsequent section will delve into what might transpire if the story proves to be more than mere fiction, if the object actually performs an unexpected action. Part 9. Worst case hypothesis. If it intersected, let us engage in a theoretical exercise, a scenario analysis rather than a prediction. What if all the prior assumptions proved correct? What if 3IATLAS, through some means, managed to alter its trajectory sufficiently to intersect with Earth? What would the implications be? Firstly, consider the parameters. Estimates for the size of 3IATLAS range from a few hundred meters to several kilometers in diameter. Certain calculations based on its luminosity and assumed albedo suggest it could be 5 kilometers across or even larger. Mass estimates exceed 30 billion tons, possibly more. This represents a colossal mass hurtling through space. Interstellar objects travel at immense velocities. Upon entering a solar system on a hyperbolic trajectory, they are not constrained by the sun's gravitational pull and thus do not decelerate significantly. 3IATLAS is currently moving at approximately 60 kilometers per second, or 60,000 meters per second, which translates to over 130,000 miles per hour. At such speeds, kinetic energy escalates dramatically. The formula for kinetic energy is straightforward. Energy equals 1/2 multiplied by mass multiplied by velocity squared. Using a conservative estimate, let us assume a mass of 30 billion tons, equivalent to 3 multiplied by 10 to the power of 13 kilograms. For velocity, let's use a midpoint estimate of 30,000 meters per second. Plugging these figures into the equation, 1/2 multiplied by 3 times 10 to the 13th power multiplied by 9 times 10 to the 8th power. This yields approximately 1.35 times 10 to the power of 22 joules. How significant is this amount of energy? 1 megaton of TNT releases about 4.2 times 10 to the power of 15 joules. Dividing the kinetic energy by this figure gives us approximately 3.2 million megatons. For context, the most powerful nuclear weapon ever detonated, the Soviet Tsar Bomba, had a yield of 50 megatons. This impact would be 60,000 times more potent. The consequences would be catastrophic. An object of this magnitude and velocity would traverse the atmosphere in mere seconds. It would not have sufficient time to decelerate or ablate substantially. It would strike the surface at nearly its full velocity, unleashing its entire kinetic energy instantaneously. The resultant explosion would dwarf any event in human history, whether natural or artificial. Firestorms would erupt across continents. The shock wave would obliterate everything within hundreds of kilometers of the impact site. Earthquakes would reverberate through the planet's crust. If the impact occurred in an ocean, tsunamis thousands of meters high would surge, traveling at jet-like speeds across ocean basins, devastating coastal cities. However, the immediate devastation is merely the prelude. The released energy would vaporize the impactor and a vast quantity of surrounding rock, soil, or water, propelling it into the atmosphere. Dust and aerosols would disperse globally within days, obscuring sunlight. Temperatures would plummet, photosynthesis would cease, and crops would fail. The ensuing famine would claim more lives than the initial impact itself. This constitutes an extinction-level event, not necessarily an extinction of all life, as Earth has endured more severe events. However, it would likely result in the demise of most large animals, including humans. We are contemplating a scenario comparable to the impact event that caused the extinction of the dinosaurs 66 million years ago. Now let us consider a less extreme scenario. Suppose 3IATLAS does not strike Earth but passes significantly closer than the projected 1.8 astronomical units. Imagine it passes at a distance of tens of thousands of kilometers, roughly the distance to geostationary satellites. What would occur then? A close flyby would still be dramatic. The object's gravitational influence would subtly alter Earth's orbit, though likely imperceptibly. Earth's significantly greater mass would ensure the effect is minimal. However, electromagnetic and plasma interactions could prove intriguing. If the object possesses a magnetic field or carries charged particles, we might witness auroras, radio disturbances, and even temporary disruptions to satellite operations. There's also the matter of debris. If 3IATLAS is shedding material either through outgassing or fragmentation, a close flyby could introduce dust and particles into Earth's atmosphere. Meteor showers could intensify, and spacecraft in low Earth orbit could face risks from impacts. The International Space Station and all orbiting satellites would require vigilant monitoring. From a scientific perspective, a close flyby would be a scientific windfall. Telescopes would capture data at unprecedented resolution, radar could map the surface, and spectroscopy could meticulously analyze its composition. If the object were indeed artificial, evidence would be undeniable at such close proximity. But let us return to the fundamental question: how much change in velocity, or delta V, would actually be required to transform the predicted miss into an intercept? The missed distance is 270 million kilometers. To bridge this gap, a substantial trajectory modification would be necessary. 86 meters per second is far from sufficient unless the geometrical alignment is extraordinarily fortuitous. Let's perform a rough estimation. The object's velocity is 60 kilometers per second. A 1% change in velocity amounts to 600 meters per second. This might shift the missed distance by a few million kilometers depending on the direction and timing of the impulse. To alter it by 270 million kilometers, a change of several kilometers per second, applied over weeks or months in a precisely calculated direction, would likely be necessary. This is not achievable with an acceleration of 0.02 millimeters per second squared over 50 days. A significantly more potent acceleration sustained for a longer duration or applied much earlier in its trajectory would be required. The numerical data do not support an intercept scenario based on the reported acceleration. Therefore, while the worst-case hypotheses are terrifying, the chain of assumptions required to reach them is extensive and tenuous. The object would need a propulsion system capable of generating immense thrust. It would have had to initiate its maneuvers months or years prior, not merely near its perihelion. It would require precise knowledge of Earth's position and velocity. And even then, the energetic considerations are formidable. If the object were artificial and deliberately targeting Earth, what would its intention be? Observation appears to be the most plausible motive. Why dispatch a probe across interstellar space only to obliterate both itself and its target in a collision? A flyby seems more logical, approaching close enough to study the planet, its atmosphere, its biosphere, and perhaps even its technological signatures before proceeding on its journey. Alternatively, perhaps it is not targeting Earth at all. Its trajectory might be coincidental, a product of gravitational dynamics within its originating star system. We may be attributing intent to randomness, perceiving patterns where none exist. What monitoring and defense capabilities do we possess? At this juncture, not many. Planetary defense systems, such as NASA's Double Asteroid Redirection Test, DART, are designed for smaller, slower-moving objects detected years in advance. An interstellar intruder traveling at 60 kilometers per second, detected only months before its closest approach, is beyond our current capacity for deflection. Early warning networks are beneficial. If we detect an object years in advance, we might have sufficient time to devise a mission strategy, perhaps even intercept it for scientific study. However, 3IATLAS was discovered in July 2025, mere months before its perihelion and approach to Earth. This is insufficient time to mount a deflection mission. Consequently, while the worst-case scenarios serve as a motivator for preparedness, they do not accurately reflect our current situation. The reality is that, according to all credible orbital calculations, 3IATLAS poses no threat. The projected missed distance is substantial, and its trajectory is well understood. Agencies are monitoring it, but they are not issuing alarms. Subsequently, we will broaden our perspective to examine the wider implications of interstellar objects for planetary defense and the study of extrasolar systems. Part 10. Broader implications for interstellar objects. Planetary defense. 3IATLAS represents only the third confirmed interstellar object ever detected. The first was Oumuamua, discovered in October 2017. The second was Borisov, found in August 2019. Prior to these discoveries, we lacked direct evidence that objects originating from other star systems ever entered ours. Now we know they do, and likely more frequently than previously estimated. The study of interstellar objects provides a unique aperture into the universe beyond our solar system. These are fragments of other worlds, remnants from planetary systems light years away, delivered to our cosmic doorstep. By analyzing their composition, structure, and behavior, we can glean insights into the chemistry and dynamics of star systems we will never physically visit. Oumuamua was enigmatic from its inception. Its elongated shape, irregular rotation, and subtle non-gravitational acceleration ignited extensive debate. Was it a comet, an asteroid, or something entirely different? Spectroscopic analysis revealed no coma, no tail, and no apparent signs of outgassing, yet it accelerated as it moved away from the sun, suggesting a force beyond gravity. Avi Loeb famously proposed it might be a solar sail, a thin reflective sheet propelled by solar radiation. Most astronomers disagreed, positing instead that it was a comet with unusual characteristics, perhaps composed of hydrogen ice or nitrogen ice that sublimates without producing a visible cloud. Borisov presented a different profile. It appeared as a conventional comet, complete with a coma, a tail, and spectroscopic signatures of water and carbon monoxide. Its behavior was entirely consistent with an icy body approaching the sun. In many respects, Borisov was reassuring, demonstrating that not every interstellar object is anomalous. Some are simply comets from elsewhere. 3IATLAS occupies a position between these two extremes. It exhibits some cometary characteristics, but also displays anomalies that do not readily fit established models. Its non-gravitational acceleration is stronger than expected for its size. The rate of mass loss, if attributable to outgassing, is exceptionally high. Its color and the potential presence of an anti-tail add further peculiarities. What does this reveal about interstellar objects in general? It indicates their diversity, suggesting we cannot assume they all conform to the behavior of solar system comets or asteroids. Their composition, structure, and formation histories likely vary depending on their origin. The dynamics of interstellar objects also challenge our understanding. How frequently do they visit? From whence do they originate? Are they ejected from planetary systems due to gravitational interactions with giant planets? Or are they remnants of star formation, material that failed to coalesce into planets? Detection rates imply that interstellar objects traverse the inner solar system more often than we had previously realized. With advancements in telescope technology and expanded sky surveys, Our detection capabilities are improving. 3ATLAS was identified by a system designed to search for near-Earth asteroids. Future surveys, such as the Vera C. Rubin Observatory, are projected to detect many more. Within a decade, we could be finding one or two such objects annually. This brings us to the critical aspect of planetary defense. While 3IATLAS currently poses no threat, the fact that bodies from outside our solar system can enter it means that future objects might approach more closely. Consequently, detection and response capabilities must be enhanced. Planetary defense against interstellar objects presents greater challenges than for objects within our solar system due to several factors. Firstly, their speed. Interstellar objects travel at significantly higher velocities, measured in tens of kilometers per second, as opposed to a few kilometers per second for solar system objects. The reduced time frame for reaction and enhanced difficulty in deflection are the first concerns. Secondly, its unpredictable nature prevents us from knowing its orbital path until it is already in our vicinity. Unlike celestial bodies within our solar system, which traverse predictable routes that we can monitor for years, interstellar visitors materialize without warning. Thirdly, the limited windows for observation mean they swiftly pass through our field of view and disappear. We may only have a matter of months to study them, making mission design paramount. If we identify an intriguing interstellar object years before it reaches its closest point to Earth, could we dispatch a spacecraft to intercept it? The answer is uncertain, contingent upon the trajectory and our preparedness. Missions such as the European Space Agency's Comet Interceptor are conceived to react promptly to ephemeral targets. Deploying additional missions of this kind, pre-positioned in space and awaiting the appearance of a target, could fundamentally alter our capacity to investigate interstellar visitors. Enhancements in radar and optical tracking would also prove beneficial. More precise astrometry leads to more accurate orbits, consequently enabling earlier detection of potential threats and a better characterization of noteworthy objects. Artificial intelligence can aid in sifting through immense data sets to identify anomalies and predict trajectories. Furthermore, there are technological spin-offs. Modeling high-velocity objects deepens our comprehension of impact physics, which has applications in material science and planetary geology. Tracking faint, rapidly moving objects pushes the boundaries of instrumentation and data processing. These advancements not only bolster planetary defense, but also benefit astronomy more broadly. Now let's consider the ramifications if 3IATLAS proves to be artificial. The impact on the search for extraterrestrial intelligence would be profound. SETI has been endeavoring to detect radio signals for decades, seeking deliberate transmissions from other civilizations. However, an interstellar probe, a physical entity dispatched across the galaxy, signifies a distinct mode of communication and exploration. It suggests a civilization that constructed machines, launched them into space, and either still exists or has left these remnants behind. Even if 3IATLAS is natural but peculiar, the implications for the formation of our solar system and extraterrestrial chemistry remain substantial. It implies that the diversity of small body physics is greater than we previously understood. It necessitates that our models of comets, asteroids, and planetesimals must incorporate a wider spectrum of compositions and behaviors. Regardless of its nature, 3IATLAS serves as a significant revelation. Whether the narrative concludes with a confirmed comet or a groundbreaking discovery, the object serves as a reminder that our solar system is not an isolated entity. The galaxy is immense, populated by countless stars and planets, and the void between them is not devoid of activity. Objects drift, collide, escape, and wander. Some of these eventually find their way here. While public fascination with alien probes can attract attention and funding to space science, it also carries the risk of miscommunication. Planetary defense organizations must judiciously manage both data and public discourse, disseminating accurate information while acknowledging inherent uncertainties. The boundary between responsible conjecture and sensationalism is delicate. Scientists like Avi navigate this boundary with deliberation, advocating for an open mind toward all possibilities. Critics contend that entertaining exotic hypotheses without sufficient empirical support erodes public confidence in scientific endeavors. This debate is constructive, reflecting the inherent tension between caution and curiosity, between conservatism and imagination. 3IATLAS, irrespective of its ultimate identification, embodies this tension. Next, we will examine recent advancements in other areas of space science that bear relevance to this narrative. Part 11. Recent breakthroughs in exoplanet atmosphere imaging. The year 2025 has proven to be a banner year for exoplanet research. The James Webb Space Telescope, inaugurated in late 2021, has spent several years fine-tuning its instruments and focusing on distant worlds. This year it achieved a remarkable feat. It captured detailed molecular signatures within the atmosphere of a Neptune-sized exoplanet orbiting a star 60 light-years away. The planet, identified as K2-18b, had been previously studied, but the infrared capabilities of JWST enabled astronomers to probe its atmosphere with unprecedented depth. The resulting spectrum revealed the presence of water vapor, methane, carbon dioxide, and hints of dimethyl sulfide, a molecule on Earth primarily generated by biological processes. This detection remains tentative, awaiting further observations for confirmation. However, if substantiated, it would represent the inaugural potential biosignature detected in an exoplanet atmosphere. The relevance to 3IATLAS lies in the fact that the same analytical techniques used for exoplanet atmospheres can be applied to the study of cometary comas and jets. Spectroscopy, the process of separating light into its constituent wavelengths, indicates the presence of specific molecules. Whether examining a planet 40 parsecs away or a comet 2 astronomical units distant, the methodology remains consistent. We are living in an era where we can scrutinize the atmospheres of remote worlds and dissect the chemistry of interstellar visitors. These tools exhibit overlap. The instruments that observe exoplanets during transits, when they pass in front of their host stars, can also be directed towards 3IATLAS to analyze its coma, jets, and any gases it might be emitting. The findings regarding the exoplanet from 2025 underscore the power of contemporary astrochemistry. Decades ago, we could barely detect exoplanets, let alone characterize their atmospheres. Now we are identifying individual molecules, assessing habitability, and searching for evidence of life. This same capability extends to closer celestial bodies. 3IATLAS could potentially offer a sample of extrasolar material, providing a direct insight into the chemistry of another star system. Its anomalous characteristics, including its acceleration, unusual coloration, and possible anti-tail, render it a significant variable. If its composition proves to be unusual, rich in molecules not observed in solar system comets, it would illuminate the diversity of planetary formation across the galaxy. The interdisciplinary nature of this research is striking. Planetary science, astronomy, instrumentation, chemistry, and physics all converge. Scientists analyzing exoplanet spectra might collaborate with those studying 3IATLAS, and the same telescopes can serve both purposes. Let us consider a specific case study. The detection of water vapor and methane in K2-18b's atmosphere involved multiple observations as the planet transited its star. Each transit yielded a spectrum indicating which wavelengths of light were absorbed by the atmosphere. By comparing these spectra, astronomers identified absorption lines corresponding to specific molecules. The required precision is extraordinary, involving the detection of molecules present in parts per million within an atmosphere hundreds of trillions of kilometers distant. Could analogous techniques reveal signs of artificiality in 3IATLAS? It is possible. If the object possesses a metallic surface, engineered materials, or unusual reflectivity, spectroscopy might detect it. Metals exhibit distinct spectral signatures. A surface composed of aluminum or steel would reflect light differently than rock and ice. Polymers, ceramics, and other manufactured substances all leave discernible fingerprints in the spectrum. If 3IATLAS were a probe, a spacecraft of some kind, its surface materials could indicate its origin. Natural objects are composed of silicates, organic compounds, and ices. Artificial objects might incorporate alloys, composites, and coatings designed for durability in the vacuum of space. These distinctions should be detectable, assuming we obtain high-resolution spectra. The same telescopes used to observe distant worlds assist us in scrutinizing nearer interstellar intruders. JWST, Hubble, and ground-based observatories equipped with adaptive optics all contribute. The synergy between exoplanet science and solar system science is one of the less appreciated aspects of modern astronomy. There is also a philosophical connection. The study of exoplanets aims to understand our place in the universe and to identify other worlds that might harbor life. The study of interstellar objects involves encountering fragments of those worlds, receiving visitors from systems we may never physically reach. Both pursuits are driven by the same fundamental question. Are we alone? If 3IATLAS is a natural phenomenon, it still acts as a messenger from another star, carrying information about its birthplace. If it is artificial, the implications are self-evident. In either scenario, it connects to the broader endeavor of searching for life and intelligence beyond Earth. Forthcoming discussions will delve into recent discoveries concerning dark matter and modified gravity theories, which could potentially shed light on how we interpret anomalous accelerations observed in small bodies like 3IATLAS. Part 12. New discoveries in dark matter or modified gravity. Earlier this year, astronomers unveiled findings from the Virasi-Rubin Observatory, which commenced operations in 2024. The observatory conducts the legacy survey of space and time, systematically imaging the entirety of the southern sky every few nights. One of its primary objectives is to map the distribution of dark matter by observing galactic clustering and the bending of light around massive structures. A recent result indicated discrepancies in galactic rotation curves that do not precisely align with standard dark matter models. Rotation curves illustrate the speed at which stars orbit a galaxy's center at varying distances. In a galaxy composed solely of visible matter, stars farther from the center would orbit more slowly, adhering to Kepler's laws. However, observations reveal they orbit at nearly the same speed as stars located closer in, suggesting the presence of more mass than is visible. This unseen mass is termed dark matter. The new data from the Rubin Observatory suggests that the distribution of dark matter in some galaxies is either more clumpy or more diffuse than current models predicted. This could imply that our understanding of dark matter is incomplete, or it might point towards modified gravity theories, which propose alternatives to general relativity that explain galactic dynamics without recourse to unseen matter. The implications are far-reaching. Dark matter is presumed to constitute approximately 85% of all matter in the universe, yet it has never been directly observed. Its presence is inferred from gravitational effects, such as the rotation of galaxies, the bending of light around galaxy clusters, and the structure of the cosmic microwave background. However, its fundamental composition remains unknown. Decades of experiments searching for dark matter particles, specifically weakly interacting massive particles, or WIMPs, have yielded no definitive results. Detectors are situated deep underground, shielded from cosmic rays, awaiting a dark matter particle to interact with an atomic nucleus. To date, no conclusive evidence has emerged. The data from the Rubin Observatory adds another layer of uncertainty. If the distribution of dark matter deviates from our models, perhaps we are missing a fundamental aspect of its behavior. Or, more radically, perhaps dark matter does not exist at all. It is conceivable that gravity itself operates differently on vast scales than we currently perceive. Modified gravity theories, such as modified Newtonian dynamics or MOND, posit that Newton's laws become inapplicable when gravitational acceleration drops to extremely low levels, as observed in the outer regions of galaxies. Instead of invoking unseen matter, these theories adjust the equations of motion. While they have shown some success in explaining galactic rotation curves without dark matter, they encounter difficulties with other observational phenomena like gravitational lensing and the cosmic microwave background. The debate between dark matter and modified gravity has persisted for decades. The majority of physicists favor the dark matter hypothesis due to its greater explanatory power across a wider range of observations and its better integration with our understanding of particle physics and cosmology. Nevertheless, the persistent lack of direct detection keeps modified gravity theories in contention. What is the connection to 3IATLAS? When we observe a non-gravitational acceleration in an object like 3IATLAS, we operate under the assumption that our model of gravity is accurate. We calculate the object's expected position based on the gravitational influence of the sun, planets, and relativistic effects. Any deviation from this prediction is categorized as non-gravitational, implying it stems from a source other than gravity. But what if our gravitational model contains subtle inaccuracies? What if there are minor corrections, unaccounted forces, or subtle effects yet to be discovered? In such a scenario, what we interpret as thrust or outgassing might actually represent a misunderstanding of the underlying physics. This is a remote possibility, but it warrants consideration. Historically, anomalies in orbital mechanics have spurred the development of new physics. The gradual shifting of Mercury's orbit, the slow rotation of its elliptical path, could not be explained by Newtonian gravity. Einstein's theory of general relativity resolved this discrepancy, demonstrating that the curvature of space-time near the sun was responsible for the observed effect. Could the anomalies observed in the trajectories of small bodies offer a similar insight? It is unlikely. The scales involved are vastly different. Dark matter and modified gravity theories are primarily concerned with galactic scales, where gravitational fields are weak and distances are immense. The inner solar system, where 3IATLAS is currently located, features strong gravitational fields dominated by the sun. Any corrections predicted by modified gravity theories would be minuscule, far smaller than the observed acceleration. To illustrate, the gravitational acceleration at Earth's orbital distance from the sun is approximately 6 millimeters per second squared. At 3IATLAS's perihelion distance of roughly 1.4 astronomical units, this acceleration is even greater. Modified gravity theories predict deviations from Newtonian gravity when accelerations fall below approximately 10 to the negative 10th meters per second squared, a value 100 million times weaker than what 3IATLAS is experiencing. Therefore, any effect attributable to modified gravity would be utterly negligible in this context. Nevertheless, the recent revelations in dark matter research serve as a reminder that our comprehension of gravity and mass is incomplete. We remain uncertain about the nature of dark matter. We have never directly detected a dark matter particle. Its existence is inferred from gravitational phenomena, but its fundamental properties are not understood. The mystery deepens when considering the cosmological scale. The universe's expansion is accelerating, a phenomenon attributed to a force we term dark energy. Similar to dark matter, its nature is unknown. It accounts for approximately 68% of the universe's energy density, yet it is entirely invisible and detectable only through its gravitational influence. Consequently, approximately 95% of the universe, comprising dark matter and dark energy, is composed of entities we do not comprehend. If our models of mass distribution are imperfect, could we be misinterpreting the accelerations caused by small forces? Could factors like radiation pressure, drag from the interplanetary medium, or interactions with the solar wind be more significant than we currently estimate? These are natural forces that do not necessitate exotic physics, but their effects might be underestimated. Sunlight exerts pressure on objects in space. This effect is minimal for large, massive bodies, but can become significant for small particles or objects with a large surface area relative to their mass. Astronomers account for this when calculating orbits, but these calculations depend on knowing the object's size, shape, and reflectivity. If these parameters are uncertain, the estimates for radiation pressure could be inaccurate. The Yarkovsky effect is another subtle force. When a rotating object absorbs sunlight, it heats up. The heated side then re-emits this energy as infrared radiation, generating a minuscule thrust. Over extended periods, this can measurably alter an object's orbit. Asteroids slowly drift inward or outward over millions of years due to the Yarkovsky effect. Again, astronomers model this phenomenon, but it requires knowledge of the object's thermal properties, rotation rate, and surface composition. Drag from the interplanetary medium is an even more subtle influence. Space is not an absolute vacuum. It contains a tenuous plasma of charged particles emanating from the sun. As objects move through this medium, they encounter a slight drag force. For most objects, this effect is negligible. However, for an object as large and fast as 3IATLAS, could it be relevant? The observed acceleration of 3IATLAS, approximately 0.02 millimeters per second squared, is extremely small. It lies at the threshold of what can be reliably measured. Minor systematic errors in astrometry, slight miscalculations of planetary perturbations, or unaccounted forces could mimic a non-gravitational acceleration. Astrometry, the precise measurement of an object's position in the sky, presents significant challenges. It involves tracking a faint point of light against a backdrop of stars, with the aim of pinpointing its location to fractions of an arc second. Atmospheric turbulence blurs the images, and telescope imperfections introduce distortions. Uncertainties in timing add noise. Even with the most advanced instruments, measurement error is inevitable. When fitting an orbit to astrometric data, a complex equation is solved, balancing the gravitational forces exerted by the sun, planets, and occasionally large asteroids. If the measurements contain subtle systematic biases, if the timestamps are slightly inaccurate, or if the star catalog used for positional reference contains errors, the resulting fitted orbit will exhibit residuals. These residuals might appear as a non-gravitational acceleration when, in reality, they are merely noise. That said, astronomers exercise considerable care. They account for known forces, including solar radiation pressure and the Yarkovsky effect, which generates a slight thrust from absorbed sunlight. They also consider planetary gravity and relativistic effects. When they report a residual acceleration, it signifies that these known factors do not sufficiently explain the observation. The Jet Propulsion Laboratory and the Atacama Large Millimeter Array are world-class facilities, and the sources of the astrometric data cited by Avi Loeb are highly reliable. Their measurements are trustworthy. The 4 arcsecond offset mentioned by Loeb is significant, well beyond the noise level. Therefore, the non-gravitational acceleration is likely genuine, not an artifact of flawed data. However, the interpretation of that acceleration and its underlying cause remains an open question. Outgassing is the prevailing explanation, but as we have discussed, this hypothesis necessitates a high rate of mass loss, which has not been definitively observed. Could there be another natural mechanism that we're overlooking? One possibility is fragmentation. If 3IATLAS is undergoing disintegration, shedding fragments as it heats up, these ejected pieces carry momentum. The resultant reactive force accelerates the main body. This process is analogous to outgassing, but driven by mechanical breakup rather than sublimation. Comets occasionally fragment, particularly when subjected to tidal forces or rapid rotation. If 3IATLAS is a rubble pile, a loosely aggregated collection of rocks and ice held together primarily by gravity, it might be inherently unstable. Another potential explanation involves electrostatic effects. Objects in space can accumulate electrical charges from the solar wind and cosmic rays. If the charge distribution is asymmetric, interactions with the interplanetary magnetic field could generate small forces. This is a speculative notion, and the effect would likely be minuscule, but it represents a natural mechanism that does not rely on outgassing or propulsion. The connection between 3IATLAS and dark matter is speculative, serving as a conceptual hook to encourage consideration of the boundaries between established and unknown physics. Could an interstellar object utilize some form of propulsion or react to an unknown ambient medium? If our models of gravity and mass are incomplete, could non-gravitational acceleration signify something other than our current understanding? Imagine the existence of a fifth fundamental force distinct from gravity, electromagnetism, and the strong and weak nuclear forces. Physicists have been searching for such fifth forces for decades, conducting high-precision experiments to verify whether gravity conforms precisely to the predictions of general relativity. To date, no definitive deviations have been confirmed, yet the possibility remains intriguing, particularly in unexplored scales or regimes. An interstellar object like 3IATLAS, originating from a different environment, might interact with forces or fields not encountered in solar system objects. Its composition, forged in another star system under distinct conditions, might include elements or structures that respond to the interplanetary medium in unexpected ways. These are thought-provoking questions, but they should not detract from more conventional explanations. Outgassing remains the leading hypothesis. The object is most likely a comet exhibiting unusual characteristics, rather than a manifestation of novel physics. The elegance of scientific inquiry lies in its reliance on empirical evidence banishing guesswork. Observations serve as the ultimate arbiters. If the object designated as 3IATLAS exhibits all characteristics typical of a comet, pronounced outgassing, a discernible coma, and spectral signatures indicative of volatile compounds, then its observed acceleration becomes readily explicable. Conversely, should these anomalies persist without any identifiable natural cause, it compels us to entertain more unconventional hypotheses. The notion of a connection to dark matter or modified gravity at this juncture leans more towards a philosophical contemplation of our incomplete cosmic understanding than a tangible, practical explanation. It serves as a potent reminder that our current grasp of the universe is far from exhaustive. We are perpetually engaged in a process of learning, discovery, and refining our conceptual frameworks. Regardless of its eventual classification, 3IATLAS represents a crucial data point within this ongoing scientific endeavor. Subsequently, we shall delve into the transformative impact of artificial intelligence on astronomical predictions and anomaly detection, potentially illuminating the true nature of 3IATLAS. This segment, the 13th in our series, focuses on AI-driven astrometric orbit prediction tools. Artificial intelligence is revolutionizing our exploration of the cosmos. Machine learning algorithms possess the remarkable ability to process immense data sets, discern intricate patterns, flag deviations, and generate predictions with unprecedented speed and precision compared to conventional methodologies. In the year 2025, a suite of novel AI-powered tools emerged for astrometry and orbit forecasting, and their influence is already becoming evident. One such innovation is OrbNet, a neural network developed through a collaborative effort involving multiple universities and international space agencies. OrbNet ingests astrometric data, observations detailing an object's spatial position over extended periods, and rigorously compares these observations against a purely gravitational model. Its output consists of residuals, which represent the discrepancies between the observed and predicted positions, and it specifically flags celestial bodies exhibiting substantial deviations. OrbNet's training regimen encompassed decades of data pertaining to asteroids and comets, enabling it to internalize what constitutes typical behavior and what does not. Upon encountering an object like 3IATLAS characterized by measurable non-gravitational acceleration, OrbNet transcends mere flagging. It proposes potential causative factors based on previously encountered patterns. These potential causes include outgassing, fragmentation events, collisions, the influence of radiation pressure, and even hypothetical, unknown propulsive forces. The significance of this lies in the fact that subtle trajectory deviations, which might be overlooked or inaccurately modeled by classical approaches, can be readily identified by AI. Human astronomers, when fitting orbits to observational data, might dismiss minor residuals, attributing them to inherent measurement noise. AI, however, with its capacity to simultaneously analyze thousands of parameters, can detect patterns that elude human perception. In the case of 3IATLAS, AI systems are actively engaged in refining its orbital trajectory, pinpointing subtle directional forces, and assisting in either refuting or substantiating hypotheses concerning potential maneuvers. Should the object's acceleration exhibit temporal variability, fluctuate with its proximity to the Sun, or display directional characteristics inconsistent with outgassing, AI will inevitably detect these discrepancies. Another significant tool, Astro AI, was introduced by the European Space Agency this year. This system employs reinforcement learning to forecast the future positions of near-Earth objects and interstellar visitors. Through intensive training on historical data and the simulation of millions of potential orbital paths, Astro AI can accurately estimate the corrective velocity adjustments required to achieve specific objectives, such as aligning with a designated target. Researchers have already leveraged Astro AI to analyze 3IATLAS by inputting the observed acceleration, its current orbital parameters, and Earth's precise location. The AI initiated simulations. These simulations explored what magnitude of velocity change, applied at a specific point in time and in a particular direction, would result in an Earth intercept on December 19th. The outcome was unequivocal. The necessary velocity change, or delta V, far exceeded the 86 meters per second figure. The calculations indicated a requirement for several kilometers per second of delta V, applied months prior with highly precise vectoring. Consequently, the assertion circulating on social media does not withstand rigorous computational modeling. This is precisely where AI demonstrates its exceptional capability. It can systematically explore an extensive parameter space, evaluating thousands of hypothetical scenarios within mere seconds. In contrast, a human astronomer might manually calculate only one or two scenarios. AI, however, computes all plausible scenarios and identifies those that are physically tenable. Nevertheless, AI is not without its limitations. Its efficacy is intrinsically tied to the quality and accuracy of the input data. If the astrometric observations suffer from systematic errors, or if the object's motion deviates significantly from the assumptions embedded within the model, AI can yield misleading results. It might flag anomalies that are not genuine or fail to detect subtle effects not present in its training datasets. Furthermore, while AI can identify correlations, it cannot always definitively establish causation. It might observe a correlation between acceleration and solar distance, suggesting outgassing, but it cannot independently ascertain the precise chemical processes driving this phenomenon. Such definitive conclusions necessitate complementary data from spectroscopy, imaging, and expert human interpretation. Consequently, the role of AI in the investigation of 3IATLAS is supportive rather than conclusive. It aids in refining orbital calculations, identifying patterns, and systematically eliminating implausible explanations. However, the ultimate determination whether the object is natural or artificial, a comet or a probe, rests upon direct observational evidence and sound scientific reasoning. An additional dimension to AI's application in astronomy warrants mention: pattern recognition within radio signals. The ongoing search for extraterrestrial intelligence generates vast quantities of data. Radio telescopes meticulously scan the heavens, capturing signals across millions of distinct frequency channels. The overwhelming majority of these detected signals constitute noise, either originating from human interference or from natural astrophysical phenomena. The identification of a genuine technosignature, an artificial signal emanating from another civilization, is akin to locating a single grain of sand on a galaxy-sized beach. AI provides crucial assistance in this endeavor. Algorithms trained to discern specific patterns amidst background noise can flag candidate signals for subsequent human scrutiny. These algorithms are adept at filtering out terrestrial interference, identifying frequency drifts consistent with transmitters on orbiting or moving platforms, and detecting modulation patterns that suggest the presence of encoded information. If 3IATLAS were indeed emitting radio signals such as the purported 1.4 gigahertz pings mentioned in social media posts, AI would almost certainly detect them. The absence of any reported detections by major observatories, despite continuous sky monitoring, constitutes compelling evidence against the existence of such signals. AI is designed to be highly effective at identifying such phenomena. If a structured radio emission were emanating from the object's direction, it would have been flagged, thoroughly analyzed, and either validated or definitively explained as interference. Consequently, predictions derived from AEI-enhanced orbit analysis suggest that by late 2025 and early 2026, we can anticipate definitive updates regarding 3IATLAS's trajectory. Residual accelerations will be quantified with exceptional precision. Any persistent non-gravitational forces will be meticulously mapped in 3 dimensions. Temporal correlations with solar distance, rotational characteristics, or other relevant factors will be identified. Furthermore, hypotheses concerning intentional maneuvers, including the claim of an Earth-directed trajectory, will be confidently either confirmed or refuted. The inherent transparency of AI tools also contributes to fostering public trust. The results generated by these systems are reproducible, allowing for independent verification by researchers worldwide. In stark contrast to proprietary models or opaque calculations, open-source AI platforms empower anyone possessing the requisite data to conduct their own analyses. This democratizes scientific inquiry, significantly impeding the proliferation of misinformation. Moving forward, we will examine advancements in radio astronomy, particularly focusing on the 1.44 gigahertz band and its implications for detecting potential technosignatures from objects like 3IATLAS. This discussion constitutes Part 14, Advances in Deep Space Radio Astronomy, 1.4 gigahertz and beyond. The field of radio astronomy has experienced a remarkable period of progress. In early 2025, the Breakthrough Listen Project, a prominent initiative dedicated to the search for technosignatures, released findings from an extensive survey encompassing millions of stars within the 1.2 to 1.8 gigahertz frequency range. This specific band includes the 1.4 gigahertz hydrogen line, a naturally occurring frequency widely considered a prime channel for interstellar communication. The survey yielded no confirmed technosignatures, but it did establish stringent limitations. It implies that if technologically advanced civilizations are actively broadcasting powerful radio signals at 1.4 gigahertz within a few thousand light years of Earth, such transmissions would have been detectable by our current instrumentation. The observed silence is thus profoundly informative, suggesting either that intelligent civilizations are exceedingly rare, they do not utilize this particular frequency band for broadcasting, their signals are too weak for our detection capabilities, or they are deliberately maintaining a silent presence. Significant progress in signal processing, the development of larger antenna arrays, and AI-driven filtering techniques have collectively enhanced the sensitivity of radio astronomy to unprecedented levels. Upcoming facilities such as the Meerkat Array in South Africa, the Very Large Array in New Mexico, and the soon-to-be-completed Square Kilometer Array are poised to further amplify this sensitivity. We are entering an era where the detection of faint radio emissions originating from nearby stars or passing celestial objects is not merely a possibility but a routine occurrence. This brings us to the specific claim circulating on social media concerning 1.4 gigahertz pings emanating from 3IATLAS. The assertion posits that the object transmitted structured signals in the vicinity of Mars, potentially serving as communication for navigation or course correction. The selection of the 1.4 gigahertz frequency is noteworthy. This frequency resides within the water hole, a relatively quiet segment of the radio spectrum characterized by minimal galactic background noise, thereby facilitating efficient signal propagation. If an advanced civilization were to deliberately transmit a signal intended for detection by others, the 1.4 gigahertz frequency would represent a logical and strategic choice. Its universality, stemming from the hydrogen line's consistent presence throughout the universe, ensures recognition by any civilization possessing radio astronomy capabilities. However, the critical issue remains. There exists no publicly accessible, peer-reviewed detection of such signals originating from 3IATLAS. Radio telescopes continuously monitor the celestial sphere. Projects such as Breakthrough Listen specifically focus on identifying transient signals, brief bursts, and anomalous emissions. If 3IATLAS were emitting 1.4 gigahertz pings of sufficient intensity to be detectable on Earth or in the vicinity of Mars, these would have been unequivocally noted. Could the signals have been too weak? This is a plausible, albeit not definitive, consideration. Radio signals diminish in intensity with distance in accordance with the inverse square law. At a distance of 1 or 2 astronomical units, a low-power transmitter might indeed fall below the detection threshold. However, this would also render it undetectable near Mars, the claimed origin point of the social media pings. Could the signals have been intermittent, consisting of brief bursts that were consequently missed? This is also a possibility. Radio observations are not perpetually continuous. Telescopes have finite observing time, and their attention is not perpetually focused on the precise location of interest at the opportune moment. A short-duration burst could potentially elude detection. Nevertheless, the complete lack of any independent corroboration serves as a significant red flag. If these purported pings were genuine, multiple observatories should have registered them by now. The fact that none have done so strongly suggests the claim is unsubstantiated. Let us now examine the plausibility of this scenario from an engineering perspective. Assuming for the sake of argument that 3IATLAS is an artificial probe, what would be required to transmit a 1.4 gigahertz signal detectable across interplanetary distances? Radio transmission necessitates both a power source and an antenna. The power output is contingent upon the transmitter's design and its energy supply. An antenna's efficiency is dictated by its physical dimensions and the wavelength of the signal. At 1.4 gigahertz, the wavelength approximates 21 centimeters. A reasonably efficient antenna could be several meters in diameter, a size that is entirely feasible for integration onto a spacecraft. If the probe is equipped with a nuclear power source or a comparably long-lived energy supply, generating several watts or even kilowatts of radio power is technologically achievable. This level of power output would be sufficient for detection at distances spanning millions of kilometers, provided a sensitive receiver and a directional antenna are employed. It is important to acknowledge that natural phenomena can also generate radio emissions. Comets, through their interaction with the solar wind, can trigger plasma instabilities that emit radio waves. Similarly, lightning events or dust clouds, if present, could potentially produce broadband radio bursts. While such occurrences are infrequent, they remain within the realm of possibility. Therefore, even if a radio signal were detected emanating from 3IATLAS, it would not automatically constitute proof of its artificial origin. A thorough analysis of the signal's structure would be imperative, searching for evidence of modulation, repetitive patterns, frequency drift, or any characteristic that suggests the presence of encoded information rather than random noise. What should we be attentive to in the ensuing weeks? Upcoming radio astronomy observation campaigns are specifically targeting the region surrounding 3IATLAS. Numerous observatories are coordinating their efforts, encompassing diverse frequency bands and observation schedules. Data release schedules are anticipated to provide preliminary results by late 2025 or early 2026. SETI, Search for Extraterrestrial Intelligence. Organizations are also actively monitoring the situation. The Breakthrough Listen project has formally added 3IATLAS to its observational targets, and if any anomalies are detected within the radio spectrum, they will undoubtedly be identified. The role of radio astronomy in this particular investigation is to either corroborate or definitively refute the technosignature hypothesis. If, despite exhaustive monitoring, no signals are detected, the claim will effectively be invalidated. Conversely, if signals are detected and subsequently verified, the scientific discourse surrounding the object will undergo a profound transformation. Radio astronomy also serves as a powerful tool for debunking. Numerous purported anomalies, ranging from fast radio bursts initially suspected of being alien transmissions to enigmatic pulses later identified as originating from microwave ovens within observatory cafeterias, have been conclusively explained by natural or terrestrial human-made sources. The scientific community in this field possesses a deeply ingrained culture of skepticism and rigorous verification, regardless of whether 3IATLAS is a natural phenomenon or an engineered artifact. Radio astronomy stands as a frontier technology for discovery. For the present moment, the discernible silence emanating from the object carries more weight than any alleged pings. Moving forward, we will conclude our investigation, summarizing our findings and outlining the anticipated developments for late 2025 and early 2026. This segment, Part 15, is a wrap-up and outlook for late 2025 and early 2026. Let us synthesize the information we have gathered. Our investigation commenced with a striking claim that 3IATLAS might be deliberately aligning its trajectory with Earth. This assertion was predicated on verifiable data, specifically a reported non-gravitational acceleration of 0.02 millimeters per second squared, and a straightforward calculation demonstrating that 50 days of such sustained acceleration could indeed result in a velocity change of 86 meters per second. The arithmetic underpinning this calculation is sound, and the observational data are factual. However, the extrapolation, the critical leap from the mere existence of acceleration to the presumption of an Earth-directed targeting, relies on a series of assumptions that remain unsubstantiated. For such a scenario to materialize, the acceleration would need to be sustained, precisely directed towards Earth, and synchronized with Earth's orbital position at an exact moment in time. None of these critical conditions have been established. We have thoroughly examined the object's projected trajectory and its predicted closest approach distance to Earth. Official sources indicate that 3IATLAS will pass Earth at an approximate distance of 1.88 astronomical units, equivalent to about 270 million kilometers, on December 19, 2025. This distance is exceptionally vast. To reorient the object's path for an Earth intercept would necessitate a significantly greater velocity change, applied over a more extended duration with extremely precise temporal coordination. The available data simply do not support the claim of an Earth alignment. We have also explored potential natural explanations for the observed acceleration. Outgassing, the process of ices sublimating and creating a propulsive force, remains the primary hypothesis. However, the mass loss rate required to produce the observed acceleration is substantial, estimated to be at least 1/16 of the object's total mass over a single month. If Avi Loeb's calculations hold true, this rate of mass loss should in turn generate a substantial coma, a phenomenon that has not yet been definitively observed by our telescopes. The jury therefore remains out on this specific explanation. We have also considered more speculative, exotic hypotheses. Could 3IATLAS be an artificial construct, an interstellar probe dispatched by another civilization? The observed acceleration, its estimated size, and its current trajectory certainly raise intriguing questions. However, there is a conspicuous absence of definitive proof. No detected radio signals, no evidence of non-volatile propulsive forces, and no irrefutable indicators of artificiality. This hypothesis, while captivating, remains purely speculative and unverified. The narrative disseminated through social media significantly amplified this claim, transforming a scientific anomaly into a dramatic account of an alien interception. This narrative spread with far greater velocity than the scientific analysis, blurring the crucial distinctions between raw data and interpretation. It serves as a poignant reminder of how information propagates in our contemporary digital age, how uncertainty can morph into spectacle, and how minds inclined to perceive patterns can readily fill observational gaps with dramatic narratives. We have also considered the hypothetical consequences should the most alarming scenario prove true that the object were indeed to intercept Earth. Such an event would undoubtedly result in catastrophic extinction-level consequences. However, the chain of assumptions required to reach this conclusion is both lengthy and inherently fragile, demanding capabilities, intent, and temporal precision that approach the implausible. Furthermore, we've broadened our perspective by contextualizing 3IATLAS within broader advancements in space science. Developments in exoplanet atmosphere imaging, research into dark matter, the refinement of AI-driven orbit prediction, and progress in radio astronomy all contribute to a richer understanding of this object's significance. This is not solely about a single celestial body. It is fundamentally about our methodologies for studying the universe, our techniques for identifying anomalies, our approaches to data interpretation, and our preparedness for unforeseen events. Therefore, what are the paramount takeaways from our investigation? Firstly, 3IATLAS represents a rare and scientifically invaluable interstellar visitor, irrespective of whether its origin is natural or artificial. Secondly, the fundamental arithmetic concerning the 86 meters per second velocity change is accurate, but it does not automatically translate to an Earth impact. Thirdly, several critical unknowns persist: the precise vector of the acceleration, its sustained duration, and its temporal alignment with Earth's orbital path. Fourthly, upcoming observations scheduled for late 2025 are of paramount importance. Data concerning mass loss, astrometric residuals, spectral analysis, and radio monitoring will collectively clarify the object's true nature. Fifthly, while worst-case scenarios are undeniably dramatic, they hinge upon numerous unverified assumptions, and official space agencies have explicitly stated that there is no perceived threat. Sixthly, advancements across multiple scientific disciplines converge on 3IATLAS, positioning it as a focal point for diverse lines of inquiry. Let us now address the timeline. Perihelion, the object's closest approach to the Sun, occurred around October 30th. The object has now passed its point of maximum solar proximity and is currently on its outward trajectory. November marks the commencement of intensified observation campaigns. As the object emerges from the Sun's glare, it becomes increasingly accessible to observation. December 19, 2025 is designated as the date of its closest approach to Earth. This is the pivotal date, the specific moment highlighted by the social media claims. By this juncture, we will have accumulated several weeks of supplementary observational data. Early 2026 will see the object in its outbound phase, with a potential distant flyby of Jupiter anticipated around March. Following this encounter, 3IATLAS will gradually recede from view, venturing deeper into the outer solar system and eventually returning to interstellar space. What aspects should you be actively monitoring? Look for official orbit updates released by NASA, the European Space Agency, and other leading space agencies. Pay close attention to any refinements and calculations regarding the missed distance and any alterations to the projected trajectory. Monitor spectroscopy results diligently. Are volatile compounds being detected? Is a coma becoming apparent? Does the object's observed color continue to deviate from expected norms? Observe imaging reports with interest. High-resolution images from observatories like the Hubble Space Telescope or the James Webb Space Telescope may reveal surface features, emanating jets, or other indicative structures. Track announcements from radio telescope facilities. Any confirmed signal detections at 1.4 gigahertz or other frequencies would represent profoundly significant news. Furthermore, observe the discernible contrast between media narratives and official scientific statements. How are mainstream news outlets reporting on this event? Do they emphasize caution and scientific rigor, or do they lean towards sensationalism? How are scientists themselves responding to the claims circulating on social media? This dynamic interplay between public perception and scientific scrutiny is an integral component of the unfolding story. If no extraordinary phenomena are observed by early 2026, what will be the implications? Will this definitively invalidate the maneuver claim? Almost certainly. If the object behaves consistently with a comet, exhibiting predictable outgassing that diminishes as it moves away from the sun, if the observed acceleration decreases or ceases, and if no radio signals are detected, then the natural explanation will prevail. 3IATLAS will then join the ranks of fascinating but ultimately unremarkable interstellar visitors. However, should anomalies persist, if the acceleration continues unabated even far from the sun, if mass loss appears minimal despite the presence of thrust, or if radio signals are definitively detected, then we will be confronted with a genuine enigma. At that juncture, exotic hypotheses will transcend mere speculation and necessitate rigorous scientific investigation. Will 3IATLAS ultimately settle into the category of an interesting yet natural phenomenon, or will it be recognized as the first confirmed engineered interstellar probe? The answer will emerge not from speculative pronouncements on social media, but from the diligent work of telescopes, the analysis of data, and the patient efforts of scientists engaged in meticulous measurement, analysis, and interpretation. One final reflection. The universe does not inherently conform to our expectations of comfort. It remains indifferent to whether we are psychologically prepared for its revelations. For centuries, humanity has progressively come to the realization that we are not unique, not central, and not cosmically alone. Every significant scientific discovery has represented a step towards greater humility. 3IATLAS, whatever its ultimate classification may be, serves as another such step on this ongoing journey of understanding. If it is indeed a comet, our knowledge of the diversity of interstellar visitors will be enriched. If it is something else entirely, it will signify that the galaxy is considerably more complex and perhaps more populated than our current imaginings suggest. In either scenario, this object serves as a potent reminder to direct our gaze upwards, to cultivate our curiosity, to continually question and to remain open to possibilities that currently lie beyond our conception. The investigation is far from concluded. Indeed, it is just commencing. The unfolding events of the next few months will determine whether the social media claims were mere flights of fancy or indicative of a more extraordinary unfolding. By early 2026, we should have a definitive answer. Until then, keep watch on the skies. The universe in its vastness is watching back.